Yeah, thanks a lot for the kind introduction, and of course also for the invitation to this very nice workshop. So hopefully you can see me and hear me well. So before I actually start, let me say that this is actually a team effort, joint project together with two former colleagues from TU Berlin, who are Jan McDonald, who is about to graduate very soon, and Max Merz, who completed his PhD last year and is looking forward to join Amazon in the role of an applied scientist very soon. Okay, so I think you also saw this very nice talk from Carola about how to use deep neural networks, deep learning for inverse problems. So I can make this introduction rather quick, and so you're already quite familiar with the subject, and I will only summarize the most important aspects that are relevant for this talk. So this slide here is really like a very basic introduction and should fix the notation for the rest of this talk. So here we will only deal with this finite dimensional linear situation for inverse problems where you're interested in the recovery of a potentially very high dimensional signal, for instance, an image, from indirect measurements. So there's a measurement process which could be modeled by a matrix, a linear forward operator, and as always, you have some noise present in your measurements, which gives you some additional perturbation. And here we will assume throughout this talk that we have a certain prior knowledge about the energy of the L2 norm of this noise. Okay, and then the question is how to recover the unknown signal given the measurements. This becomes particularly interesting, if the problem is ill-posed. So for instance, there could be less measurements than free variables. So some information is missing, and without any further assumptions, it's impossible to solve. So typical problem is in painting, and this is really closer to what we will see in this talk, the example of compressed sensing MRI, where you're interested in recovery somatical image from highly undersampled frequency measurements. So in general, we have this quest for unique and stable solutions. Okay, but I guess this is nothing new for you. Also, what is not so new for you due to Carola's talk, is how to solve these inverse problems with deep learning. So here in this slide, you really see like the most important points, which I find most relevant in this subject. So I think the main difference to classical variational approaches is that, in the most extreme regime of deep learning for inverse problems, what you would like to have is a reconstruction map that is very explicit. It's just a map that takes the indirect measurements and spits out some hopefully good reconstruction. And there are some learnable parameters that you would like to compute from training data. So in the supervised case, you would assume a very large data set with examples from your inverse problem. And basically what you do is some empirical risk minimization that tries to fit your training data and thereby computes good parameters for your reconstruction map. And hopefully all this will generalize very well to unseen data. So, typically, we will see examples later on, more concrete examples later on. This will be a neural network. So it's a very explicit map. So it will be very fast to be evaluated, but it could model very complicated dependencies. So it could give us a highly nonlinear reconstruction. Okay. And another important thing is that in this vanilla form, where you really have this end-to-end learning, all the prior knowledge is basically inferred directly from the data. So this stands in contrast to this classic idea of handcrafted regularization. However, and I think I should point out this here, typically what you have is a combination of learned components like convolutional neural networks or building blocks, and also more model-based components which involve the forward model. And again, I later on in this talk, you will see some more concrete examples about this. Okay, so
just a short comment. So, prior knowledge, if you also consider the architecture or whatever, in some sense, this is also prior knowledge.
That's true, right? So, for instance, there's this idea of the deep image prior, which is in a somewhat different regime, but in principle, you could also use that things like prior knowledge. But here I'm really comparing this to classical handcrafted prior. So basically, you only infer your problem-specific knowledge from the data. Okay, but this is really an extreme regime.
There's still some form of prior knowledge that you still, put into and not directly from the data.
Yeah. Okay, so maybe, I mean, I will let me maybe do this comparison, and I mean, maybe this is also what you've just seen is like an extreme regime, right? So this is really like this end-to-end approach where you really like learn everything end-to-end, and there's also something in between. I think this became much clearer in this talk from Carola, that there are also like compromises between like fully end-to-end approaches and classical variational methods, like the adversarial regularizer, for instance. But nevertheless, let me do this quick comparison. And again, this is nothing new, but just to like motivate what you will actually see in the rest of the talk. So, okay, so I think one important point in favor of neural networks is that in many cases of interest, they simply lead to better results, to higher quality results. And often they're also faster because, at least in the end-to-end case, you have an explicit reconstruction map, which stands in contrast to variational approaches where you actually have to solve an optimization problem. Okay, and also like typically you will have a mismatch between your handcrafted prior and the data that you're interested in. Okay, but nothing is for free. So the expensive part here, of course, is the training. So you need good training data, you need high quality training data. This is typically a big issue. And even if you have the training data, what you will get is something very task specific, right? So it will be highly adapted to the problem that you're interested in, whereas classical variational approaches are more universal, I would say. So if you have a good prior, like let's say TV, you can use it for many different types of problems and it will give you decent results. Okay, and finally, and I think this is most important for the rest of this talk, is like this striking gap between our fundamental understanding for both regimes. So like one point that was also very well pointed out by Carola was like, for these end-to-end neural networks, and this will be the focus of what you will see here, unfortunately, only or most results that we have are still only empirical. So unfortunately, we still have to treat these neural networks largely as a black box. And this is really different from classical variational approaches where we have a rich theoretical foundation, like compressed sensing, for instance, we have optimization theories. So I think it's fair to say that nowadays these are quite well understood. To be a bit more precise about this, so what you would be interested in, of course, is control over the error that your reconstruction method makes. So basically, by a simple triangle decomposition, you can like identify two terms that are relevant here. So I call them accuracy and robustness. Maybe in compressed sensing, this would be rather called stability, compressibility. But in any case, so this term refers to the idea of reconstructing the signal well in the ideal situation where there is no noise in the data. Right? So for instance, for sparse recovery, know that in certain situations, perfect recovery is possible. And on the other hand, what is also, of course, very, very important is to analyze the sensitivity against noise in the measurements. So this is what I refer to as robustness. Okay, and so ideally what we would like to have are error bounds of this form, right? So we would like to control the error in terms of the noise level, which is the prior knowledge that we assume here. And if you're familiar with compressed sensing, at least in some situations, you are really able to derive such error bounds. Okay, but unfortunately for end-to-end neural networks, such things are not available yet. So we still have to rely on empirical assessment. So here in this talk, I will mostly focus on the aspect of robustness. Okay, so let's speak about that. Before I come back to this problem, let us just zoom out for a second or for one slide and then give you like a historical overview of well, what role is played by robustness in deep learning in general. So I think about 10 years ago, this whole hype with deep learning, in particular in classification, started, and quickly after it turned out that these deep neural network classifiers, although leading to outstanding results, are quite vulnerable against adversarial attacks. So maybe you've seen this image of this panda bear before, where you basically have a deep learning classifier, which is completely fooled by just computing a tiny perturbation to your input. So this panda bear is perturbed. It still looks for us as humans like a panda bear, but the neural network is completely fooled. And what you basically exploit here is some gradient-based information. So you assume excess on the weights, and you basically compute some tiny perturbation that maximizes like the misclassification of the neural network. And the intuition, at least which I have here, is that for some reason the high dimensional decision boundary is quite brittle. So that seems to be an issue here. But well, I think this is like still a very active and ongoing field of research. So we have this arms race between people who invent new types of adversarial attacks and also countermeasures like defenses. And there are thousands of papers, and at least as I know, there is no final conclusion about this yet. So it's still active. However, most of these results are concerned with classification and related tasks. So it turns out for inverse problems, much less is known, although recently there are a few very interesting papers have appeared analyzing this aspect. And this is also what we will deal with for the rest of this talk. Okay, so I think one of the most influential papers in this field is by Anton and al., which I think recently appeared in PNAS. And they made so their conclusions were quite worrying. So this picture, which you see here, is taken from their paper. And so basically what they did here from technical perspective, they adapted this idea of adversarial attacks to the regime of inverse problems. So what they did is they computed some perturbation to the input that should maximize the reconstruction error of the neural network which you use here. So in this case here, it's the AutoMap, which is a pre-trained model, which they simply took like from the literature. And so what you see here is, okay, well, they basically visualized this perturbation which was computed not in the measurement domain, but in the image domain. And what you see is if you then measure this image, you take the measurements and let the neural network do the reconstruction, suddenly some artifacts appear. So in their conclusion basically was, well, this seems to be a tiny perturbation in the input and they are striking artifacts in the output. There seems to be some kind of instability here. And when we saw this, basically this was also like the starting point of our project. So what we were wondering about is like typically what you see in like talks about inverse problems are error metrics like PSNR, SSIM, L2 error. So when we saw this paper, basically this was something that we missed there. So what we were wondering about is like, is there a quantitative theory or quantitative analysis that we can make? So what does tiny here actually mean? So how tiny is this in numbers, right? So that was like the main question that we were asking in the beginning. And so the goal of our project was to say, well, maybe we can come up with a quantitative error analysis of robustness and see if these issues which appear here are really so bad, or well, what is actually going on there. So this is what the rest of this talk will deal with. So our findings with respect to a quantitative analysis. Okay, so before I can show you some results, we briefly need to speak about like the experimental design. So again, this will be nothing new after Carola's talk. So the first approach that we consider is, I think, historically one of the first that also appeared in literature. It's very simple. We call it post-processing neural network. It's a simple two-step procedure. We basically, what you do is you take your measurements. Here it's the compressed sensing MRI example. You first do a very cheap model-based reconstruction, which here is just a zero filling of the missing measurements and taking the inverse Fourier transform. So you will get a result, a reconstruction, an image, but it looks very bad due to a non-trivial kernel. So this is not acceptable. And what you do is you train your neural network to enhance this image, right? To denoise or to remove these artifacts, and hopefully you will get a clean reconstruction. So it's very simple, but well, for when this appeared, I think this was still quite impressive and very cool. Of course, you can do more fancy stuff. So you could like replace these components. So here, I forgot to say this, typically, so one typical choice of neural network would be a fully convolutional one, which is the famous UNet. But of course, you could replace this by something else, something that is even more powerful. Maybe you've heard about this. It's called the tiramisu. You can just think of a more powerful version of the UNet here. So you can hope for better results. And you could also make additional components learnable, like this first linear inversion. It's a linear layer. You could try to make this learnable and again, hope for better results. So it's a fully learned neural network. And finally, and I think when it comes to neural networks, this is really like the state of the art. You could use some iterative approach. You could make more use of the fact that you have some knowledge about your inverse problem. You know the forward model, you would like to make use of this. Okay, so what is the inspiration here are really classical schemes that you would use to solve some variational problems. It's, for instance, a proximal gradient scheme. So basically you can view this iterative scheme, the finitely and many iterations, as a neural network. What you can do is you can make some of these components learnable. So for instance, you could replace the proximal operator by a neural network, which here in our case is just a unit. Okay, and then you still have these data consistency terms, which are basically just the L2 gradient updates from this iterative scheme. So this hopefully encourages some additional data consistency because it involves the forward model. Okay, so that's a more fancy architecture, but I think nowadays quite well established. So what was important here is that we trained all these neural networks in-house, all by ourselves, and really like with standard training, empirical risk minimization with Adam. In particular, what was very important to us, no adversarial defenses involved. So this is not like a project about adversarial defenses, but really about the robustness of like common architectures in the field. Maybe just like a side remark, this iterative network, which you see is really not, I think, not a toy example. So it's a simple architecture, but in fact, you can really achieve state-of-the-art results with this. So in principle, you can train them such that you will end up like in the first place of some leaderboards in some public challenges in the field, in particular when it comes to computed tomography. Okay. Well, that's one thing. The other thing is, of course, like how do we measure robustness? Okay, so conceptually, the idea is quite simple. So what we do is we say, well, adversarial noise basically is worst case noise. So the worst possible perturbation that could occur. So what you do is you compute that perturbation to your input measurement, so to the noiseless one, which maximizes the reconstruction error of your method, which here is the neural network. Okay, and you do this within the noise constraint, right? So this is like the prior assumption that we have. So if we can solve this, basically you will get the worst error when it with respect to L2, right? So it's really a quantitative measure. Okay, I should say this is non-convex, so we have to rely on approximate solutions. So we solve this by unrolling, or not by unrolling, by automatic differentiation in combination with some projected gradient descent scheme. Okay, but even if you're able to solve this perfectly, it's still not so clear what to do with it. Right, so it's still like you have this worst case perturbation, but it's still not clear how bad this is. So and here, I think like the main idea comes into play of this whole project, which is to say, well, the nice thing for inverse problems is we know that there exist robust methods, which are the classical variational methods. So we know in compressed sensing, we even have such error bounds, right? So for instance, for TV minimization, which was the main method here in this project, but you could also consider alternatives here. And the point is, okay, we know that these methods are robust, and we know that at least in some situations we have error bounds. So maybe there's a way to compare the robustness to such classical benchmarks. So again, I mean, this is just an error bound. We don't know the worst case noise. So what we would have to do is to compute also worst case perturbations for such methods. So then we have something to compare to. Right, so basically we are trying to reach the limits of such error bounds by computing worst case noise. So the idea is simple, but I can tell you technically it's not so simple, because here basically what you would do is you would replace the neural network by like a method like TV minimization, which apparently leads to a bilevel optimization problem, and that's not so easy. So this, I think, from a technical perspective, this was like the main difficulty of this whole project, to come up with like a good approximate solution here. So I think we succeeded in the end. So basically it's based on some non-trivial unrolling of TV minimization by an ADMM scheme. So that was like the main technical idea here. Okay, so with this at hand, I can now show you some results. So let's start simple with a classical compressed sensing example. So here, really in this regime where we have standard Gaussian measurements, like so in this regime, which is nowadays quite well understood from a theoretical perspective, the signals are synthetic, just one-dimensional piecewise constant functions with random jumps. And then basically, we analyze the robustness with such types of signals. Okay, so here is just one example where we perturb TV minimization adversarially. So in the noises case, because TV is a perfect match, you won't see any error. You get perfect recovery, which is very consistent with compressed sensing theory. And well, if you increase the noise and compute the worst case perturbation, of course, the error is growing. So as you can see here, and already a 6% adversarial noise, you will see like, well, the error is like about 2.5 times large. And also qualitatively, the solution is really not acceptable anymore. So even though this method is robust, provably robust, we can stop it. So the noise is simply too large. Okay, so that's just the benchmark. So let's see what the new networks are doing. So here's this post-processing one based on the UNet. Okay, so you don't get perfect recovery in the noiseless case. This is maybe something that you cannot expect from such simple methods. This is in some sense also related to the aspect of accuracy. But what is like somewhat surprising is that if you increase the noise, the error is not exploding. Actually, it behaves quite similar to that of TV minimization, and also qualitatively, like the perturbed solutions look similar, right? So in some sense, it's comparable. And if you use more expressive models like the fully learned one or the iterative network, it only gets better. Okay, so this is just, again, pictures. So you can do this more systematically over more samples in the test set. So what you get is these noise to error curves, right? So where you plot the adversarial noise against TL2 error. Basically, this just confirms what you have just seen. The robustness of the learned methods are really comparable to that of TV minimization, which is good. Okay, and also here,
these are all exclusively empirical experiments.
Sorry, I didn't understand the question so well acoustically.
These are all empirical experiments, right?
Yes.
Okay, thank you.
Yeah. So that's the point, right? So we unfortunately don't have any error bounds. Or okay, in this situation, we might be able to at least have a rigorous error bound for TV minimization, but not for the new networks. That's like, in some sense, we would like to use like this robustness from TV minimization, compare it to the new networks. Yeah, but all what you see is completely empirical. Okay, and also like what you see here is there is really a gap between Gaussian noise and adversarial noise. Okay, so you see like the slope of TV minimization is, I don't know, about a factor 3 or so. Okay, cool. And of course, you should do this more for more complicated data sets. So here basically is an overview of the other case studies that you will find in the paper. So we did this for MNIST, which is also pretty standard. So here, what is interesting is TV is not a perfect match anymore. So it is the new networks outperform TV regarding both accuracy and robustness. And I think the reason is they simply adapt better to the data, right? So that's a difference to these synthetic piecewise constant signals. And then we moved on to real image signals, much higher dimensional. So it's well related to compressed sensing MRI. So here's still synthetic data, which are these random ellipses. So in a way, the counterpart to these piecewise constant functions in 1D, but the picture qualitatively isn't very much the same as in the 1D case. And finally, this is nowadays quite popular, the Facebook NYU fastMRI dataset for MRI. Essentially, that's like a more higher dimensional counterpart for MNIST, right? So essentially, the picture here is very much the same. The new networks adapt better to the data, and we get improved accuracy and robustness. Okay, so for the remaining time of my talk, what I would like to give you an impression of is like, okay, so you might wonder now, okay, so these are the numbers. So this is what we were aiming at, like a quantitative error analysis, but you might still wonder, so what is going on maybe here at the very end, at the right end of these curves? So here's a picture for worst case reconstructions for this synthetic ellipsis example. Okay, so it's for the ITNet and for TV. So you see like both solutions are not really good. So, well, you see here these ellipsoidal artifacts, and for TV, you clearly see like this amplification of the oil painting effect. You might be worried, well, maybe these are some instabilities, right? So maybe, I don't know, the network is hallucinating somewhere here. So what is going on here? So what we did to check this is very simple. We took the perturbation computed for the ITNet, and just plugged it into TV. And what you see here are the same ellipsoidal artifacts, right? So it's basically the same artifacts appear in a completely different model-based method. So our conclusion here is, well, basically the only thing that the attacker did with this 8% budget of noise is to add some additional features to the data, which not very surprisingly look like ellipses. So that is what happened here. So these are real features. This is no like hallucination or instability. Interestingly, the reverse experiment did not succeed in the sense that the oil painting effect did not carry over to the learned method. So we don't have an explanation here, but this is how it is. But I think like from this perspective of robustness, this one here on the top is more important. Okay, so finally, you might be also wondering, so I've motivated all this with this paper from Anton et al. And you might be wondering, well, how is all this connected, right? So is this like a contradiction? So I think, so my main explanation here is that when it comes to the experiments, I think we can really reproduce their findings. So basically what you see here is like the same experiments then that they did in their paper. So what we did is we took the adversarial perturbations for both the ITNet and TV minimization. We did a zero filling and took the inverse Fourier transform, and this is what you will get. So basically, that's the perturbation for the highest noise level in the image domain. And I don't know if you can see this very well on the screen, but okay, you might see some ellipsoidal artifacts here, but for TV minimization, it looks quite good. But then if you like measure and let the reconstruction happening, you will see these artifacts. Okay, so basically like there are issues in both regimes if you want. So I think the main reason here is that this is not really like related to the particular method that you're using, but in some sense related to the ill-posedness of the inverse problem, right? So in terms of numbers, I think everything is okay, right? So, well, the error is increasing, but well, in terms of numbers, it's pretty much the same as you can see here. So our conclusion is again, like, this is really like related to the ill-posedness of the inverse problem to a non-trivial kernel rather than the fact that if you're learning using a learned method or a model-based one. Okay, so I think I'm running out of time. So here's the conclusion. So I think the three most important takeaways are as follows. So one hand, of course, is like this, at least for us, it was somewhat surprising to see that these reconstruction methods based on deep neural networks are quite robust and that you can achieve this without any adversarial defenses. And finally, of course, like what we needed to like verify is this benchmark method. So this was really like the key here, to have some benchmark to compare to. And we more relied on a quantitative analysis than just a visual inspection. Okay, but okay, to be fair, of course, this I think is really just like a minimal criterion for more reliable use. So I think there are many, many open questions. So basically, this is just, again, quantitative error analysis with respect to the L2 norm or some other measures like PSNR or SSI, which you also saw on the slides. But still, I mean, there are questions open like, so why do we have apparently this gap between classification and reconstruction? So it's not so clear. What about out of distribution features? So particular data, some features in the data that are very tiny, but very important. So it might be still consistent with our idea of L2 robustness, but might be a big issue for radiologists, right? Or also these hallucinations, right? That there might be something in the data which is not really there. Okay, so this is like from a more empirical side. And of course, what would be very great to have are some certificate at least to verify that at least the local Lipschitz constant of these neural networks at the points that you're interested in, at the data that you're interested in, is controllable. Okay, so I think I'm done here. So the paper is in the archive. We're also very happy that it was recently accepted at TEPAMI. The code is online, so you can play around with this, and I'm happy to take your questions.